Okay, we're back for one more example, and this time we're going to use MATLAB a bunch so you don't have to watch me invert a bunch of matrices. Okay, this is a two-tank mixing problem. You probably remember this from your ODEs class. It has a bunch of details. We really just use this to draw up a picture. So I'm going to read through this, but I can't draw a picture and show you the words, so you can see the words on your PDF, and I'm going to read the words and draw a picture down here. So I have two tanks, right? Tank 1 and tank 2. Okay, so tank 1 initially has 200 pounds of salt, and it is 1,000 gallons of water. And tank 2 just starts out with fresh, 1,000 gallons of water and 0 pounds of salt. What we're going to end up looking at is these Q1 and Q2, which are concentrations, sorry, not concentrations, amounts of salt in each of these tanks. So it's going to be like pounds that we're looking for, right? So this is, let this be an amount. This means pounds, LBS. Okay, starting at time equal to 0, salt water with a concentration of 1/5 pounds per gallon flows into tank 1. So I have an inflow of 1/5 pounds per gallon at a rate of 10 gallons per minute. And saltwater concentration of 1/2 pounds per gallon flows into tank 2 at 10 gallons per minute. Great. This solution is now well mixed, Q1 and Q2, and it flows out in two different ways. It flows from tank 1 to tank 2 at a rate of 10 gallons per minute, and it flows from 2 to 1 at 10 gallons per minute. Then it also pours out of tank 1 at 10 gallons per minute, and same for tank 2. What you may remember from your class is that we can use this diagram to write a differential equation. So something that looked like this. I would say, what is the rate of change of the amount of salt in tank 1? Well, I start off with some fixed amount, right? So that doesn't matter for the rate of change. But I have some constant amount flowing in. So 1/5 pound per gallon, but I want this as a rate of change of pounds. So I have to multiply it by the rate in gallons per minute. It's the right units. Then I'm going to add salt in from tank 2. So whatever the concentration is in tank 2. So Q2 is the amount of salt in tank 2 divided by 1,000 gallons. This is in pounds per gallon. And again, we need a rate, 10 gallons per minute. And then I'm going to lose salt, both going out of here and going out of here. So the rate, if I sum them up, is 20 gallons per minute. So I'm going to subtract the concentration Q1 over 1,000 gallons and pounds are the units times 20. That's 20 pounds per minute, or sorry, 20 gallons per minute. So this gives us something that looks like 10 divided by 5, so 2 plus 10 divided by 1,000, it's 1 over 100 Q2 minus 20 over 1,000 is 1 over 50 Q1. Hopefully that rings some bells. So if I look at the first line of this equation up here that I want to verify, I have minus 1 over 50 times the first element, Q1, plus 1 over 100 times Q2, second element Q, plus 2. Awesome. The initial condition, 20 pounds of salt versus 0 pounds of salt, and the second equation, hopefully you can just kind of walk through this diagram and see that that also satisfies here. So this is the equation that we're looking for. If we solve this, we can understand how the amounts of salt, Q1 and Q2, in those tanks change in time. Okay, excellent. So let's do some stuff which ultimately ends in us finding solutions to this equation. I'll step through it in pieces. So part one is we have this linear system, which we just formulated. Let's find all the equilibria for this. So equilibria are going to be the places where the right-hand side equals 0, right? So I need to solve AQ plus B is equal to 0. So Q, I'll put a little E for equilibria, I guess these are vectors, is going to be minus A inverse times B. This guy here, and I'm just going to use MATLAB to do that, because I think that you have seen quite enough of the hand stuff. Okay, so you can see MATLAB, I think. So A is minus 1 over 50, 1 over 100, 1 over 100, minus 1 over 50. That looks right. B is 2, 5. And I want to solve minus A to the minus 1 times B, the parentheses, just to be on the safe side. And so the equilibrium is 300 and 400. This is going to be pounds. 300 and 400 pounds of salt in each tank. So that's what we're looking for here. Using MATLAB. Great. Apply a stability analysis about the system. What does the analysis tell you about Q of t? So what should we look for? We should look for the sign of the real part of the eigenvalues of A. So eigs of A, let's go back to MATLAB, be a lot more expedient. Okay, so eig A, two negative numbers, tells me that this equilibrium should be globally asymptotically stable from last lecture. So eigs of A are both real. They were real, right? Check. Yep. And less than 0. Last lecture shows that QE is globally asymptotically stable. So stable means solutions don't go far from it. Asymptotically stable means solutions approach it, they start close. Globally asymptotically stable means regardless of your initial condition, you will approach this equilibrium. So that is where we're going to end up. Okay. So let's find a general solution corresponding, this is part 3, page 10 in your notes, corresponding to the homogeneous linear system. So we had the eigenvalues, and then we get the eigenvectors. So let's take a look at that. Maybe they have kind of a nicer form. So the eigenvalues, where lambda 1 is minus 0.03. I'm just reading off of my MATLAB. Lambda 2 is minus 0.01. What are the eigenvectors? MATLAB is probably going to give it to us in a wonky, normalized form. So that we can just take a look. Back to sharing. So I'm going to now put in the 2 arguments of MATLAB, where the first is the eigenvectors and the second is the eigenvalues. Actually, we're pretty lucky. So what's this form? This is really 1, 1 divided by its norm, right? 1, 1 divided by the norm of 1, 1 gives us this. That's 1 over the square root of 2, right? So the eigenvector corresponding to 0.03 is 1 minus 1, and the eigenvector corresponding to minus 0.01 is just 1, 1. So I've written that down on my paper. I'll show you that now so you can see that here. So these are the eigenvectors. So the general solution is a linear combination of these. So QC of t is C1 e to the minus 0.03t, 1 minus 1, plus C2 e to the minus 0.01t, 1, 1. Great. So let's conclude number 4 here. The general solution of the non-homogeneous linear system is this junk. Okay, so QC, these two terms here is what we just found, right? 3 over 100 and 1 over 100. So that's what we just saw. And then what we talked about last class is that because the non-homogeneous equation looks like ax plus b, we're adding a constant. And so the constant term that we get in the non-homogeneous solution is actually just the equilibrium. So we talked about that in class, and then I think that we talked about it also, we talked about that in the recorded lecture and then also in the recorded Q&A from last Thursday. So this is going to be the equilibrium, what we found before. Awesome. So now we know what the general solution should be for the homogeneous in part 3 and for the non-homogeneous in part 4. Okay, so since equilibrium is globally asymptotically stable, for the theorem from last lecture, we know that independent of C1 and C2, we should end up there. And that looks to be true, right? If I look at these dynamics, it doesn't matter how big or small C1 and C2 are, because these exponential functions are going to decay, right? So these first two summands are going to die, and I'm just going to be left with this regardless. I hope that that makes sense. Okay, and so we can solve an initial value problem and then look at what the solution looks like and show that at least that one does respect the result that we find. So I have the same non-homogeneous equation, and say I start off with the initial conditions that we set in the problem: 200 pounds of salt in tank 1, nothing in tank 2. So QT is going to be C1, 1 minus 1, plus C2, 1, 1, plus 300, 400, and that should equal 200 and 0. So the system of equations is C1 plus C2, and then 300 plus 300 is equal to 200, so it's minus 100, and minus C1 plus C2 is equal to minus 400 here. We can use MATLAB to solve this too, right? This is really C1, C2 is minus 300, minus 400. This guy, oops, sorry, minus 100 and minus 400 here, and times the inverse of the matrix from here, which should be 1, 1, minus 1, 1, inverse. Whoops, there we go. Let's use MATLAB to solve that too. Let's call our A now 1, 1, minus 1, 1. Let's do A, inverse, times minus 100, oops, minus 400, whoop. And a semicolon, cool. And so I get that C1 should be 150 and C2 should be minus 250. And so that's my Q of T, whatever that is, 150 e to the minus 0.03t11, 1 minus 1, minus 250. Well, you can recopy this if you want to. It doesn't really matter. Plus the equilibrium. And so here's a plot. I start at 0 and 200. So the 1 is a solid line, 200, 2 is this line. And where does it saturate? It saturates where this one goes to 300, this one goes to 400 as time goes forward. So that looks good, and that's all for today's lecture.